Okay, so for this one here, okay, our diagram is going to look like this. We've got these two logs. Okay, the second one is 250 kilograms. Okay, and the first one that it's attached to is smaller. It's only 150 kilograms, and then that's attached to the horses. Okay. So what the question tells us is the horses pull with a force of 2,600 newtons. Okay, so that force is 2,600 newtons. Okay, the force of friction on the whole system is 2,400 newtons. Okay, so if I simplified this, right, I'd be looking at 400 kilograms with 2,600 newtons going this way and 2,400 newtons going this way. Everybody okay with that? Okay. Calculate the acceleration of the logs. Well, that's pretty straightforward, right? I just have to do sum of all forces and then F times ma, or F equals m times a, and I've got the acceleration of the whole system. So that's probably an important first step. So I'm just going to find my F net by going vector sum of all forces. 2,600 minus 2,400 is 200 newtons. Okay, and then I'm going to say acceleration is F net over m, so 200 divided by 400. That gives me 0.5 meters per second squared forward. Okay, so I've got an important piece of information now about not only the whole system, but about each part of it as well. Each one of those logs individually accelerates at 0.5 meters per second squared. Okay, so now comes part B. The force of friction on log A is 900 newtons. Calculate the force exerted by log B on log A. All right, well, let's look at log A. Log A, we have more information about than log B. Okay, if I'm just looking at log B, the only information I have about log B is, well, nothing. I don't know how much force is being pulled forward on it. I don't know how much friction is resisting. I could calculate it, but I don't really want to because there's no point. Okay, I'm going to solve this using log A, which is the 150 kilogram log. I know there's 2,600 newtons from the horses pulling forward. I know there's 900 newtons acting backwards due to friction. Are there any other forces acting backwards? Yes. What is it? Log B. Yeah, the force they want to find. What's the force exerted by log B on log A? Well, log B has to resist. Okay, so this is the force of B on A. Everybody follow my logic there? Okay, so those are the forces acting on the 150 kilogram mass. And what else can I calculate about the 150 kilogram mass? What? Okay, I actually already know the acceleration. I want to use it. What can I calculate with the acceleration and this? F net, right. I can find the net force acting on the first log. So F net equals m times a. 150 times 0.5 is 75 newtons. All right, so I know my net force is 75 newtons. And I know that my net force is 2,600 newtons plus negative 900 newtons plus the force of B on A. All right, I want to find the force of B on A, so I've got to move these two numbers over here by subtracting them. All right, so my net force is 75 newtons minus 2,600 newtons minus negative 900 newtons equals the force of B on A. All right, so I've got 75 minus 2,600, okay, because those are both forward, minus negative 900, that one's backwards, okay, which leaves me with 1,625 newtons backwards. Perfect. That should be a backwards force. Log B would be pulling backwards on log A. Okay? Now I only have 3 significant figures, I think, here, so I've got to make this 1.63 times 10 to the 3 newtons backward. Okay? So does that question look like all the other examples we did on Friday? Right? They were all multiple pieces in a system, and we were using the fact that if something is pulling on something else, there's always a reactive force. Remember, there's always those action-reaction pairs. So if I know the whole system, I can use action-reaction pairs within the system to calculate different numbers using different boxes, et cetera, et cetera. Okay, so that's all there is to Newton's third law. Okay. All right, questions on that one? Okay, I want you to try a really easy one. This one's much easier than these system questions we've been doing. Okay? While standing on a horizontal frictionless surface, let's say ice, okay, two students, A and B, push against each other. Student A has a mass of 38 kilograms, and during the push, accelerates east at 0.6 meters per second squared. Student B is accelerating west during the push at a rate of 0.75 meters per second squared. We're looking for student B's mass. Okay, so they're standing together, okay, and they just put their hands up like this, put their hands together, and one of them pushes. Okay, so imagine what would happen after that. Okay, we know the mass and the acceleration of one of them. We only know the acceleration of the other, and we're looking for that person's mass. Okay, think about action-reaction pairs. Someone pushes on someone else. That someone else does what? Pushes back with an equal but opposite force. Okay. Okay, so like we said, this one's relatively easy simply because we know that there's only two objects involved and they're actually directly acting on each other. Right? There's none of this, well, one's pulling the other or whatever. Okay? We know one exerts a force on the other. That force is going to be equal but opposite from the other one. So we're going to have student A here, who's 38 kilograms, who's accelerating this way, okay, at 0.6 meters per second squared, okay, because of the force exerted here, right? The other person is accelerating that way because of that same force. Their acceleration is 0.75 meters per second squared, but I don't know their mass. Okay, just looking at this situation, is student B lighter or heavier? Lighter. Their acceleration is bigger, so they're obviously lighter. Okay, can I calculate the force that is acting on student A? Yeah. They told me that this is a frictionless surface, so the only force involved is the one that was exerted by the students. Okay, so I can take my 38 and multiply by 0.6. Right, and there we go. I've got the force, 22.8 newtons. Okay, so the force that was exerted is 22.8 newtons. Okay, sorry, that should go right here. This force is 22.8 newtons. So what's this force? 22.8 newtons. That's the only part, that's the only thing that's involved with Newton's third law in this question. The rest of it is all Newton's second law. As long as I remember forces act in pairs, now I can do an F equals m times a calculation over here. Everybody follow on that? Okay, so mass equals F net over m, so that'll be 22.8 divided by 0.75, and I should get 30 kilograms, okay, for that. Everybody all right with that? Pretty straightforward. Okay, see if you guys can do that one. Pretty straightforward, like 2 steps. Okay, I think you guys can handle it. It's got a little acceleration stuff in it you'll have to do. Okay, a little bit of kinematics, acceleration formula stuff. Okay, so we've got a force of 125 newtons. Okay, 125 newtons. We're told the mass, okay, 50 kilograms. And we're told VI, 0 meters per second. We're told the time, 0.110 seconds. And what can we find with F net and mass? Acceleration. Okay, now I'm saying this is F net. It's really the force this person exerted on the wall to the east. The force exerted on them is really 125 newtons west. Okay, so I'm going to calculate the acceleration and know that it's west. So 125 over 50 should be 2.5, right? Okay, so I've got an acceleration of 2.5 meters per second squared to the west. Okay, I know VI, I know T, okay? Now I know A, and I'm looking for VF. All right, so I'm simply going to use this formula, VF minus VI over T, and I'm going to manipulate for VF. So A times T minus VI, sorry, plus VI, equals VF. Okay, so that'll be 2.5 times 0.110 minus 0. So really it's 2.5 A times that. So we got 0.275 meters per second west. That should say west after it. Okay, everybody all right with that? Most of the time Newton's second law is kind of, or sorry, Newton's third law is like that. Okay, rarely is it like the multiple boxes remembering the forces act in pairs. You still have to remember forces act in pairs for a question like this. Okay, but more often than not, these are kind of what you see for Newton's second law. Okay. Questions on those?